Hi, everyone. I'm Christian Allinson. I'm a first-year LGO in the ECS department, and I'm going to be sharing a bit about my experience with industrial automation, predictive maintenance, and kind of what's been taking so long for this to catch on. My button works. So I'll talk a bit about my own background and what I've done that has given me kind of these insights. A bit about the maintenance process and how we think about it from the industrial standpoint, what predictive maintenance is and why it fills a lot of the kind of inefficiencies in the current maintenance process, the mismatch that's prevented it from really becoming mainstream, and then some ways that this can be fixed in the future. So definitely feel free to interrupt me with any questions. So about myself, before coming to MIT, I worked for Chevron for about 7 years as a control systems and automation engineer. I did a mixture of roles, R&D, technology qualification. I worked in our major capital projects for a bit doing startup and commissioning, and then spent a few years in base business doing run and maintain. So in that time, I've been a few places. I worked on offshore deepwater production platforms in the Gulf of Mexico, in our downstream and chemicals organization. This is the El Segundo refinery just south of LAX. I grew up a bit in a water treatment plant we were building in New Mexico, and then spent the last few years of my time doing lots and lots of fun things in the Central Valley of California. This is the Kern River oil field. If you ever see a stock photo of just pumping units for like a newspaper article or something, it's a pretty good chance it's a picture from this field. So if you look at, or if you get into operations in industry, things kind of go into two different buckets. One is operations, the people that are actually running the equipment, making the product, and then the maintenance side, the people that are making sure that equipment runs. And from kind of the project lifecycle perspective, if you're an engineer, maintenance is really not the fun part. The stuff is the fun part. So say you have a cool project, it's funded, you're doing a lot of interesting engineering and design work, you're building things, you're turning it on, you're making it all work, you're beating expectations and coming out ahead. And at some point in there, you have to go to the maintenance workshop and talk about how to keep all this cool stuff you just built going long term. But then you shake hands and high five and move on. And really the small font for that bullet 5 is how much attention is put on maintenance usually in projects, even though it is undeniably critical. Without maintenance, you wouldn't have working assets, but it's not really a role that attracts a lot of people into it. It's not really exciting. A lot of it's a mixture of paper wrangling. You're looking at maybe like your manufacturer's recommendations for how to maintain equipment, maybe some interest like industry standards, just trying to keep a good plan going. And there's points where you really have to be kind of a hyper subject matter expert. So like if you're a maintenance engineer working on things like fixed equipment or pipelines, you have to know a lot about erosion and useful life of fixed equipment. It's not really the most glamorous part of the industry. And really going into a maintenance role, you're already in a position where you're starting with trade-offs. Really, maintenance is one big trade-off. You typically have a lot of stuff, but you don't really have a lot of time. Even if you did have a lot of time, you'd probably have even less money to work on all this stuff. So what happens is maintenance starts with kind of your prioritization of what things are actually worth it to pay attention to, and what things are you going to let just run and run and run until they break, and then you can decide to fix it or repair it or just leave it be. So for an example, say you're coming into looking at how you're going to prioritize your maintenance, and you have a given piece of equipment. You're really trying to answer two questions. How likely is it to break? Is it, maybe something like a big tank will run 30 years before you really have to do something to it? Or is it a really high pressure, finely tuned compressor that maybe only a year or two without really having to look at it? And the other question you're asking is, how bad would it be if it actually broke? And bad can mean a few different things. One is like, what's the lost production? You have to have this piece of equipment to run your plant. Maybe bad is how expensive it is to repair it. So maybe it's not mega critical to producing whatever you're producing, but it's $500,000 and you'd rather not break it. Or maybe it's super long lead time. There's a lot of very customized things out there that might take 6 months or longer to get a replacement for if you actually let it break. And what this kind of comes down to is you have how likely is it to break on one axis and how bad would it be if it broke on the other. You're prioritizing. You're saying, how much effort does this thing really garner out of the limited time and resources that I have? Or is the answer it doesn't get any attention at all, and we're just going to let it break? So this comes into these two different ways of setting up your maintenance organization. The preventative maintenance, usually what people, or at least what I think of when I think of PM, is that it has enough criticality, it warrants some kind of continuing attention. Things unlike pumps, you're going to, replace lube and bearings and stuff like that. Instrumentation gets bumped and calibrated to make sure it's actually reading the way you think it's reading. Valves that don't move very much, you're going to stroke test them, make sure they actually open all the way and close all the way when they need to. Or the stuff that you're just going to let it kind of run to failure. Things like little small dosing pumps, convenience instrumentation, things that are really expendable that just aren't worth it. They're either not worth it to the process or they're not worth it to try and stop it from failing because it's so easy to repair. And part of the consideration this also goes into is, say it does break, what do you have to do to fix it? And this comes into kind of two flavors as well. There's in situ repair where your process can be running around you. Maybe it's something that's redundant or you can bypass it or it's just nice to have. And you can fix it without really having any other mitigations in place. But what is more common, especially in complicated environments like refineries, is that you have to wait for something called like a turnaround. So this is stuff that can only really be repaired when everything's down. So I don't know if turnaround's a common term in other industries too, except for refining, but it's this event that happens every maybe 4 to 5 years where you kind of close the door for a month. You turn everything off, you take it all apart when it needs to be taken apart, you fix it up, you put it back together. You hope you got everything that needs to be done because you don't have another chance for 5 years. So this is the idea that you're going to be doing maintenance whether it needs it or not. And this is for either critical pieces of equipment that you can't run the process without it. Things like maybe big electrical feeder circuits where you're getting all your power from, some of your utility and control systems, or stuff that you really just can't do anything without or while the rest of the process is running. So the mesh of these things together creates this kind of maintenance environment that is very, very not optimal. The stuff that feels more important than maybe the mean, you're pushing to this higher tier of, we're going to put more attention on it to make sure we're looking at it, we're repairing it when we get the chance, it's going, it's not going to break, or we're not going to let it break. We're just going to keep it moving. And the stuff that feels a little less important than the mean, that you could just let it break. So it's just kind of like you're pushing these two things to extremes, and you may not be actually repairing things that are on the verge of breaking. So you may be wasting time, or you having things that are breaking that you're really kind of relying that you'll notice it and be able to find it and repair it. So it feels like there should be a better way to do this, right? We shouldn't have to just rely on these preventative maintenance or run to failure kind of two decisions. And especially with where industry is today, it's not like there's no data out there. The digitization of industry is decades old. Many of the sensors and stuff that are deployed right now are very smart. They can do some form of self-diagnostics. They can tell you if things are about to go wrong. A lot of important equipment like big compressors or pumps have very sophisticated monitoring systems, like vibration monitoring is common on big stuff that looks at the vibration frequency or the frequencies and the vibration, shut it down if things are about to get bad. And digital control systems are also prolific. Anything you really want to measure and collect, you should be able to. used to sit in my office in Houston and watch what they were doing in offshore Angola in real time. I mean, this data gets around. And it's not like the algorithms or means to do some of these things are absent at all. Even simple regressions are out there. Learning methods, classification methods are equally prolific. So shouldn't by now all of this have really come together to make something better? And that something better should be predictive maintenance, the other PM, where the idea that you're not just trying to keep things going to prevent a failure, but you can actually predict when a failure is imminent and do more of a just-in-time repair. And there's obvious benefits off, over the normal status quo. Over preventative maintenance, you're reducing the kind of low incremental benefit things you're doing. Like in a turnaround, you're not doing this repair just because you can't for another few years. You're not really sure if it's going to fail in the next 5 years, so you're going to do the repair and hope for the best. And the obvious benefit over run to failure, where the stuff that's kind of forgotten until it goes wrong, you can now bring it back into the fold and make it part of some sort of monitored maintenance plan. So the idea with predictive maintenance should be that you're making the whole thing a little bit more optimal. You're not wasting time on things that don't need it. And with some of that time you buy back, you can put it on things that you otherwise would have just forgotten. And say that you're like me, you're an engineer with a hard hat, and maybe you're not super up on data science or machine learning techniques. You think there should be some products for this out there, right? And the answer is yes. For one, MathWorks has a predictive maintenance toolbox that goes in the MATLAB, and it provides kind of the things that you would expect from maybe a predictive maintenance platform, some nice histograms and stuff. There seems to be very focused on like rotating equipment. So there's a lot of stuff about vibration and bearings and gears and stuff in there. But also kind of think about that MATLAB and what MathWorks is putting out is very generalized in terms of kind of the breadth of industry and users it uses. So this isn't a toolkit that's really made to like plug into industrial automation systems. This is a very broad reaching thing. So there's probably a lot of work that needs to happen to get this data in. And once, predictions are generated, get it out into a way that works in our normal workflow, like if it's a work order, whatever. So shouldn't there be other things from other vendors? So looking at more of an automation company, Rockwell Automation loves to tout that they are used by the top 80, 90, 100% of the top clients in industry, and I believe them entirely. And they've tried to tout some things like an innovation suite, realizing the full value of predictive maintenance. But if you actually try to figure out what they're doing and what that actually means, it's pretty hard to. All their links are dead. So it seems like even though they recognize that this is at least a business opportunity for them, they don't care enough to actually keep it up. One thing I did find that actually looks pretty cool is this is a picture from Maximo. That's a computerized maintenance management system, a CMMS. Usually in industry, you have this kind of system that has a record of all your stuff, like all your pumps and equipment, whatever, and the information about them, when you bought them, what the specs on it, stuff like that. And it also has the service history attached to it, so you can see work orders, preventative maintenance tasks, all that kind of stuff. So it's kind of like your running record of all your assets. And this looks pretty cool. You can see there's a criticality, there's a risk, even a prediction of the next failure. So great, problem solved, right? But this means that you have to kind of buy into the Maximo ecosystem, which is not a trivial task. This isn't really like a small plug-in thing that you can choose. I was trying to think of an analogy, and I think deciding, like from an industrial setting, deciding to go with Maximo just to get this toolbox is kind of like deciding you're going to move to France because you want to drink wine. It's not a very, it is a answer, but it's not something that's taken lightly. And if you're not doing it already, there's a good chance you're not going to. So there's stuff out there. And if you then ask, is anyone using them? I think the answer is not really. So I worked in our central engineering for Chevron. Our scope was the entire company. So my years there, my years in base business, going to industry conferences, talking to many, many, many vendors, there doesn't seem to be many like really good foundational products or solutions that enable predictive maintenance. And of the ones that are being used by people, they seem to be very, very niche and very, very high touch. So I can say in my time, we did not have really what you might consider like learning models for predictive maintenance at all. And why is this? I mean, we seem to have plenty of data or the ability to capture data, and there seems to be plenty of things we can do with that data. So why isn't it being done? And in my mind, it kind of comes down to two things. The first is organizational capability, which I won't really talk about much past this, but really a lot of the engineers in industry, they don't have a lot of data science or machine learning background. Oil and gas is kind of special that it does have fairly high salaries, but comparing like what you'll make at a pulp and paper mill to what you'll make at Google, being asked to do the same kind of thing, you're not really being compensated the same. So even if there are people that have those skills in the company, they're, I'd say on average, not the closest ones to the equipment. So it makes it hard to get that information and see those problems and actually do something about them. And I'll give some examples in a few slides. And the other is kind of where conventional automation design has gone. Automation got, I think it started, pretty heavy in maybe like 80s, 90s when computers were becoming more prolific. But the idea of all these vendors that you're going to buy something and put it all together is that all these things are really built to communicate anonymous time series values. And I'll give an example of that in one slide. If you do have something more specialized that gives something more than an anonymous time series value, the interoperability of those systems is low. You take, for example, a package that is really good at telling you the health of like your pumps. Maybe, or probably your average scenario is that what comes out of that is like a PDF file, not really something that's useful for creating models or any learning things with. It's really meant to be consumed by like human engineering eyes at the end, not by another system. And the last piece is data fragmentation. And that's the idea that you have all these pieces of data that kind of relate the health and life cycle of your asset, but they're just all over the place. And I'll give an example of that as well. So imagine this is your little factory. You've got your stuff that actually interfaces with the process down here. In this example, I'm going to say we have a pump, and this pump is flowing at 200 gallons per minute. If you look at this sensor reading in relation to the controller, it looks something like this. That has no context of what it is on average. If you're using an older system, it's word and register based, like this is a Modbus address. It really doesn't mean anything. You just know that somewhere in memory is the number 200. Modern systems do have text-based tag names, so you can get some context. But then if you look at it from this computer system, which is maybe like a computer in a control room that the operators use to watch the pump, it has a different name. It has something called pump1.flow, and it's pointing to this controller and it's pointing to this piece in memory. And maybe since there's more than one pump, they're adding some elaboration on the tag name, but really it's the same thing. You're pointing to an arbitrary space and getting a number, and up here kind of disconnected, assigning it context. And it only gets worse the higher you go up. You're storing this stuff maybe up here in a database, and this database probably covers more than one plant. So now you're adding more context to it. And really nothing is actually kind of consistently connecting these things together, except this long line of like pointers back to this number 200. So it gets hard, especially as you expand, to keep track of what all is going on. The context of what stuff is doesn't really flow through the system. It's a very manual effort. So you have all like your description, your engineering units and stuff like that up here. But if you change something down here, this is all going to point to that piece in space, and it might never get updated. So that's kind of the idea of like this anonymous time series value passing. You're just passing this number 200 around, and by sheer physical, human effort, keeping it all consistent. And to make things a little bit worse, like we talked about your maintenance system, say you have all your maintenance records for that pump in here, it has all that information, has nothing to do with the values getting recorded. It could be called something else entirely. So just this data fragmentation of all these places that like you have information that could be useful for doing anything with predictive maintenance, but it's spread out over different places, and there's nothing kind of internally consistent keeping it all together. And hopefully to highlight that a bit more, I have two kind of use cases that I've come across in my career. The first example is from something called a dyno card. So this is a rod pumping unit. I'm sure you saw hundreds of them on my first picture. And it is an incredibly common form of lifting. So if you have, this is hopefully the only oil talk I'll do. If you have a reservoir that doesn't have enough pressure to push its own fluids to the surface, you use a lifting technique, like a rod pump. And all this does is there's a little check valve down here. On the downstroke, it pushes this plunger down. On the upstroke, it pulls this column of fluid up with it. They typically run completely unattended. There's a little controller on it that senses when there's enough fluid in here to make it worth turning it on, and it pumps it down. And it just does that over and over. But to kind of keep track of the health of it and what it's doing, there's something called a load cell that's attached right here. And it's just reading the force that it takes to do that upstroke and that downstroke. And the graph of that over the length of time it takes to do the stroke is called a dyno card. And it looks something like this. I'm not going to pretend to know how to read it, but hopefully the shapes will be very obvious. So this is a good dyno card. Everything is flat and happy and stable. So maybe this is the upstroke and that's the downstroke. So this is a perfect card. But if things start to go wrong, the shape of that trend starts to change. So if this is if a perfect rectangle is a good card, this is a worn out pump. And maybe there's something else, like this is from a hole. So it should be obvious that looking at these cards, you can tell pretty quickly that something's different, and these shapes and patterns are consistent across like this common failure mode or bad thing across different pumps. So this should seem like kind of a prime opportunity to do, if not just like an image classification to say what these cards are doing, but maybe some predictive maintenance. This card's probably not going to change from one stroke a rectangle to one stroke a little wing. It's probably going to deteriorate, and you can use that to do prediction on failures. So the benefit of this would be massive. When I was working for Chevron in the Central Valley, we operated over 10,000 wells, which means we have over 10,000 pumping units out there continuously making dyno cards. And they run about 25% of the time. And I think a stroke takes about 30 seconds. So you can imagine how many cards are produced every day, let alone every week or year. But we're not really doing much with them. An engineer will look at it occasionally if they have reason to believe that there's an issue with that pumping unit, but it's kind of an eyes-on activity. They have to specifically look at it and interpret what that card's telling them. And what's preventing this from being kind of turned into this streaming learning thing is largely the automation system. The automation system is built to transfer anonymous time series values. So something like this card that's better presented as an image, at least to us, can't transfer that. say you wanted to stream this information as a time series value where you're plotting it over time and you can recreate that shape. I guess a stroke takes about 30 seconds. And if you look at a card, I'm going to guess 100 data points over 30 seconds to really recreate the shape and do something useful for it, maybe more. If you're lucky with typical like industrial radios, you can get one value every, if you're really lucky, every second. On probably more typically, you're getting it every 15, 30 to 60 seconds, which means that the data throughput just isn't there to be able to recreate that information. So it's not a function of information not being there or available. It's really that the connecting pieces to this, even though it seems so obvious, have not been expanded or really fixed to enable these what seem like pretty obvious techniques to do predictive maintenance, let alone just kind of health recognition. And another example for this is on digital valve controllers. So this is a pneumatic valve. The way they work is this will get, this little gray box is a valve controller. This will get a set point from the actual like process controller saying open this 50%. This will add air onto the top of this diaphragm. It'll push the stem down and make this little ball go up and down to put it where it needs to be. When it gets a signal to open, it vents the air, a little spring pushes it back up. So this is kind of like a sub controller. And they are incredibly intelligent as far as end devices go. They have a large degree of internal measurements and diagnostics, not only to describe the state of the controller itself, but actually the state of the valve and kind of like the physical pieces. So if you think of a valve, stiction is a big issue where you have to add, like if the stem starts to stick, you have to add a lot more air to actually make it move, or let off a lot more air than you tend to see to make it move. You might get like this big like swing if your valve stem's sticking. That's an indication of failure. All these other stuff about like the little solenoid electronics and stuff. So massive amount of information in these things. And valves are, especially in downstream and chemicals, incredibly important to safe operation. If your valve doesn't, if you have a safety valve or certain process control valves that maybe live their life in one little band, and there's an event or something where it needs to go full open or full close and it doesn't because it gets stuck, you could have catastrophic consequences to that. So very, very big reasons to make sure that your valves are reliable. So there should be all kinds of information that you want to look at in these valve controllers to make sure things are going on. And it pretty much labels the data for you. This thing gives out alerts saying that there's pressure problems or stiction problems, all that kinds of stuff you can use to do any number of supervised learning. And it's really, really scalable. There's very few models of these DVCs used. So if you kind of crack this for one or two types, you can apply this to hundreds to thousands of valves. And again, the question is, why isn't this done? And the answer is that there's no scalable way to retrieve this data. Not really any at all. And the reason for that is, again, this anonymous time series values that everything is kind of built with in mind. Instruments, even today, are almost universally connected by a 4 to 20 milliamp current loop. The instrument or device will modulate that current to communicate information. Usually it's represents a signal between 0% and 100% of span. There is a way to digitally superimpose some information on top of that current loop, and it's called HART. Very common, very standard in many things. But the problem is that HART also focuses on anonymous time series values. There's 4 primary analog variables that most things, like that's kind of like the bare minimum of HART. You can get those 4 primary variables back and forth, which if you read, looking at this, there's not 4, there's more. And depending on your device, there could be many, many more. So HART, the standard way of using HART, you're kind of restricting yourself to only a subset of information if you want that stuff out. And kind of what these diagnostics are in these devices for are for the technicians, but they're not really meant to be collected, and they're not really meant to be historized. They're meant for a valve technician who walks up with his handheld communicator or his laptop, can punch open a little application, and it'll tell him everything that's going on. And it's supposed to be used just then and there, and then it sits all this information until the next technician comes up and punches it in. So there's some solutions for getting this data, like scalably and historizing it, but very few, if any, are actually in active development. And this is just one example for one class of device. But if you think of any, like arguably any industrial device you have that's doing measurement or control in some way, it has the exact same problem. If you think about like what's running a motor, if you have like a motor protection relay that knows like the voltage and current that's going into that motor. It might even have like power factor or be wired up to the things measuring temperature inside the motor. It has all this information, but usually the only signal that comes out of that thing is the motor's running and if it tripped, because that's the only thing the operator needs to know about. So all this stuff is really designed around what does the operator need to see. And the problem is that I think automation keeps digging in one direction. And to really get industry to a point where the things that are very common and, maybe in commercial or things that aren't so, I don't know if risk conscious is the right word, but where you don't have pumps and valves, and pipes and stuff, is that these kind of prolific paradigms need to be broken. So apart from the organizational capability part, the technology stack that's used in industry really needs to embrace this idea of devices as their own thing, devices having identity and states that move around on their own without a lot of extra work, and the abstraction of data, getting away from the idea that the only thing that exists is time series value, like time series scalar values. Device identity is big when you start to look at things at scale. If you run a smaller facility and you have a handful of pumps and a handful of valves, it might not be so hard to keep track of where everything is. But as you scale up and look at larger facilities or even companies of multiple facilities, it becomes very, very hard to keep everything in line, especially with things that are built over various spans of time, different kind of de facto standards that, when it went in, things do not really line up. So the identity of that device really needs to come with the data. It can't be something that is handled separately. And the other is, again, the abstraction of data. So scalar values have their place, but they're hugely restrictive. Hopefully the Dyno card example made that seem pretty clear. So transporting generalized data structures really needs to be embraced. Everything right now is, like I said, around moving the value 200 around. So there's a few things that are promising about where industry is going and what might kind of change this to enable not only predictive maintenance, but any number of other modern ideas. One is MQTT, message queuing telemetry transport. Rather than being a pull response kind of thing, it's a publisher subscriber protocol. But the nice thing about it is that all of the kind of context of the device comes with it. So when, this isn't a great picture, it was the best one I can find. It's like, say this is one device. It has a measurement of temperature and humidity. If it's connecting to this broker is not asking it, saying, I only care about your temperature, give me your temperature. It's saying, here's all my stuff. You can have a record that I have it And if anyone wants it, they can connect to you and pull it, which is vastly different from the current state where this says, give me that one value in that one place. And that's the only thing that people have the option to get. There's a variant of MQTT called SparkPlugB that introduces some of the things that are desirable from an industrial setting. A big one is like birth and death tracking. So when a device comes online and goes offline, you really want to know that if you're running your plant off these devices, maybe not as much as if you're using it as you like your thermostat. It's been developed by Arlen Nipper at Cirrus Link, and Arlen was one of the original developers of MQTT, which was actually developed in the oil fields. It was made to connect remote pipelines through costly satellite links in a very effective way. He says that people didn't really start caring about it until Facebook published a blog post saying they were using MQTT to power Facebook Messenger. So now he's happy again. If you ever go to a conference and see an older guy in all denim, that's probably Arlen. The other one that is becoming, or kind of changing this paradigm is Opc Ua. This stands for Opc Unified Architecture, and it's the next generation of what used to be kind of the de facto standard of communicating time series data between systems. And the idea of it is that it can be everything to everybody. And if you look at all these little blocks in it, it's not just time series values. You can have your own data types, you can have views of objects, Dayton has methods that you can define methods that are executed on remote systems. So really it's pulling in all this stuff that, okay, now I can really abstract data and I can present it the way that I want, and the communication protocol will take care of moving it around. In reality, it's kind of turned into it's nothing to nobody. It's been a huge chicken and egg problem that hardware companies are waiting for a software company to support it, and software companies are waiting for hardware companies to provide it. So even though it's been out since 2008, close to no products actually implement it. And if they do, all the ones I've seen only are using it to transfer time series data. So all this cool stuff about it has kind of gone to the wayside. So here's where to go, is that the current architecture paradigm really needs to be broken and rebuilt. I think what is preventing predictive maintenance from becoming a big thing in industry isn't the technology of the devices. It's not the technology of actually doing the predictions. It's the pieces in between. It's this idea that what's really been going on for the last, I don't know, 10 or 20 years is that legacy protocols are being wrapped in something that runs on Ethernet. It does the same thing from the end user's perspective as it did when it was RS-230 or 232. So the protocols need to get more, be more flexible. And the end devices really need to be seen as kind of first-class citizens. So currently the paradigm is that like controllers are the gatekeepers of this stuff. The controller will read what the controller needs to read. Anything else is kind of stranded. The controller reports what it needs to enable safe and reliable operation of the facility. But all this great stuff that's been added at kind of the two extreme ends of the automation space just do not have a way of being communicated to each other. So that's my impression of it. I think there is good work that's happening. There are some companies that are getting really innovative on ways to connect this stuff, but until this kind of paradigm of how you treat devices and how you connect them is either like revolutionized in place or completely broken, it seems challenging to actually make predictive maintenance a reality in industry. And that's all I've got. Any questions?
I have a question. This is great. This is great. Just the challenges throughout the whole stack are amazing. Do you think there's any opportunity to, I guess, leverage maybe it's almost, you know, consumer devices, or, you know, something that, you know, I don't know, home automation systems, home devices, or something like that, you know, there's a bigger driver for, and, you know, maybe they're evolving fast on a faster cycle or anything like that to then leverage that towards industrial applications.
Yeah, I really think there is. And I think that's been appreciated. At least it was becoming it when I was at Chevron. So like this slide kind of gives you, this is conventional automation, where the idea is that you don't want to have anything exposed. You're keeping everything really, really low down. And it's kind of like two tin cans and a string is what you can pass information with through your firewall. Because you don't want people coming the other way and reconfiguring stuff and, you know, potentially causing loss of life. So that makes the consumer stuff kind of restrictive, where a lot of development is cloud connected devices, you're using common carriers, cellular, stuff like that. So what I've seen is kind of this parallel box that we're starting to say is acceptable. Everything on this side is what is for integral to the process and the process safety, no cloud, cellular, whatever. But the stuff is more like nice to have, like maybe dyno card data, where, you know, it's just telemetry. This stuff we can use all those consumer things for. And I think that's, I've seen a lot of that with MQTT as well. I think all of the big companies that are embracing like IoT, you know, as a service or just supporting it, they're using MQTT because it brings us benefits. And there's a blossoming ecosystem of devices that use it for industry. So I think that's correct. I think it is that stuff that's coming back from the commercial space. It's a mixture of what actually like kind of passes the test of being able to withstand the industrial space. That's, you know, a product problem. The other is getting or doing it the right way so that you're not creating you know, safety or security issues by implementing them.
Yeah, because it also reminds me, I'm trying to remember what conference it was, but I heard an excellent keynote, I think, on embedded devices at one of the circuit. You know, Luca, you might, it was, you know, ICCAD or DAC or something like that. And it was a talk by companies working on embedded devices saying, you know, embedded devices, especially again for consumer kinds of things like your handheld electronics or your DVD player or all of these things. And the whole point of the talk was actually what you just mentioned of you have to build in all kinds of capability. And it was like 6 or 8, 10 different kinds of modules or chips that you have to have, including especially security. And he was making the big play. It's always got to be updatable. You know, you put it out. So it just thought that, you know, there were a couple of these companies that were trying to, you know, have the packages or the design infrastructure to embed such things in consumer electronics that, again, might also be transferable, because it starts to become the same problem of much more appreciation about security, privacy, need for encryption, and so on. So it just reminded me a lot of that talk.
Yeah, and those are things that we had almost not incidents, but kind of opened up the door we shouldn't have for this. So there's not in any of these pictures, but on like these pump off controllers, there's usually like one radio that goes to our system. And there was some other people, this is kind of a war story, but another team that like, well, we want more data and we want the stuff that you guys aren't collecting. And the vendor said, oh, we can just pop on our radio and we'll collect it and we'll give it to you as a service. Like, great. So this is a group that doesn't have anything to do with security or IT or automation kind of agreeing to do this because they're the ones that own these pumping units. And what has unintentionally happened is that a third-party service provider is sharing wires with us into our process control network. So this kind of idea of like, yes, it's really easy, but if it's not done the right way, you've kind of crossed the streams of security and insecurity.
Question, how impactful do you think like a really really like strong case study would be to like spur hardware and software upgrades that would like allow for this data to flow? I guess what I'm trying to get at is it seems like there are technical challenges to getting data in the right form to do the type of modeling that would enable predictive maintenance. And it seems like maybe one of the problems is that those upgrades aren't happening because the companies can't really measure the benefit of doing those upgrades.
I think it would be very helpful. So right before I left, we were a big Microsoft company. So this whole thing that started to come up was this might actually not be agreeing with you, even though I think it is. But like we started like deploying like Power BI and all these kind of desktop data tools to everyone, like forms and stuff. And the way it was like branded was like citizen developers, where anyone can have a good idea, think of something, show its value, and just like the fact that people were using it and it was driving a work process was, proof of existence that it's a good idea, rather than doing like a, business case study and stuff like that. So I think that having a good case study of why this is important would be very valuable. What I have seen though is that a lot of the cases that seem to come up focus on the same things. They very, very often seem to focus on rotating equipment, because rotating equipment is like well understood and it's kind of easy to narrow down. It's a lot of thing about like vibration studies, electrical voltage and current studies, transient stuff like that. So people seem to know that, yeah, we can do cool stuff with pumps and compressors, but we'll get there when we get there. I don't think what has been shown is what we were saying, like by opening that, like having like a sandbox for this stuff, that these kind of novel ideas that like, if you didn't know what a dyno card was, you'd probably never think of this as a solution or like as a problem you can solve with some of these techniques. So as much as I think case studies are helpful, I don't know, it seems like it's kind of the other way. It's like give people or let people like gripe about it, tell them, give them some ideas like what could be done, and they'll say, oh, I have a problem I think could be solved with that. And maybe that's the way to go. I'm not sure if that really answers it all.
Yeah, I guess I'm sort of curious, like at Chevron, how much money would it have taken to get these systems in a state where, for example, you could actually pull this data in a way that you could model it and give like an actionable alert. It sounds like the technology might exist, but it's just expensive.
Yeah, it's a good question. I think I was in a lucky spot to not be exposed to that side of things too often. My ideas of a good time were fairly cheap and obtainable on the technology side of things. So I was able to go and do a lot of stuff with low cost and impact. So I have a lot of experience on that side of things. But I think like the relative to, like for this example, the relative benefit that if you're deploying this on 10,000 pieces of equipment, even if it costs maybe, if you do a pilot and it costs $1,000 to do 200, like $1,000 each to do a few hundred. That's not terrible when the idea is you could completely revitalize or like reimagine your maintenance process, or you have contract technician.
That's sort of my point, is that it does seems likely to me that you could upgrade the data transfer systems in a cost-effective way if it enabled predictive maintenance with enough benefit. And I'm wondering if the reason that it hasn't been done is because it's actually hard to measure that benefit without someone else having done it before you.
Gotcha.
And like, maybe that's what everyone's thinking.
I think the other question is like, do you upgrade it to what?
Well, okay, so that's what I was wondering.
Yeah.
Is the technology not there?
Yeah, I don't think it entirely is. I think like the closest you get to it is stuff that feels more consumer than industrial, and it is hard to get it completely vetted.
Okay.
You did mention that sort of ecosystem that you could buy into at the beginning.
So,
yeah. Do you think that it would take something like this in order to get good data organization structure adopted, or do you think that it could slowly sort of be built up over time?
I think it could be built up over time, because just the way that this is designed, like I said, it's just an incredibly manual effort of just like pointing things at each other and then trying to remember what it means at the end. So I don't think the answer is necessarily Maximo or a system like that, because that doesn't really solve this problem, where the state and the context and the identity of this device is like hand coded all the way up until it gets to like wherever Maximo lives. So I think it's like, it could definitely be a good platform if like to get all that stuff together and actually have kind of like one pane of glass, so to speak, to look at for everything. But I don't think it's actually solving the problem of all that context not coming with it.
Do you think that there sort of could be a top-down solution, or is there a top-down solution maybe to organizing all of this and keeping the context, or has that not been developed
I really
yet?
think it needs to be bottom up, because so like when I was working, let me go back to my pretty picture of the river. So like stuff would just pop up here weekly. They might put in a new gauging site, they might put in a new steam generator, they might put in a new like steam splitter. And to keep track of all that stuff, there's, you know, a whole administrative process where you build the tags for it, you build the, you know, you put it in inventory, build up the asset ID, assign it preventative maintenance tasks, all that kind of stuff. And very often it does not completely work because someone forgets to send an email or someone doesn't follow up on something, and you've lost what that thing right there was. And I mean, there's so much stuff you can't really tell what you don't know about. So something I did before I left that I think is really cool, so I like to brag about it, but I wrote some software that would go out and scan every IP address on our network and find these controllers. And I would send them the commands that made them self-identify. And it would tell me what they were, what the name of the running program was, if they were healthy or not. And I just like put that on a little map with dots in Power BI. And that's in my mind, like 1,000% improvement over what was being done, which was when a controller is added in the field, you have to specifically create tags here with the idea of I'm going to point at health data in here. And if like it times out or it goes bad, I've configured an alarm and someone's going to notice it and do something about it. So it's a very top-down, like that was a top-down approach, and it's just not that sustainable. So I think bottom-up is the right way to do it.
Gotcha. That makes a lot of sense.
any other questions I can answer or thoughts?
You mentioned, the use of radios and so on. I mean, it seems like in especially these large scale kinds of operations and plants, you need, some kind of, wireless connectivity. Is that just a good assumption here?
Yeah, so
That may
in
even
this
be true in a factory, by the way.
yeah, so out here, I was lucky that Kern River was fairly, I'm not going to say it doesn't have a lot of hills, because it obviously does, but it doesn't have as extreme terrain as some of the other fields did. But all of these, you can't really see it. Like this tiny little tank right here has a programmable logic controller on it. All of our PLCs were on Ethernet radios. So we just plugged it. It was like an Ethernet bridge, and we could pretty much get any data we wanted. So all of the remote sites are connected with Ethernet radios. If it is a critical enough thing, it'll be hardwired with copper or fiber. All of the pumping units, though, were on serial radios. So much lower capacity to transmit data and a lot more congestion on the network, because as you can tell, there's thousands of these things. So yeah, radios are definitely out there. I think I think the connection medium wasn't always the problem, because if we had, if it made sense to put something on these pump off controllers so that we could have the bandwidth to send image data, we had the technology's there. It's just that little controller can't represent that as an image to something that can connect to it on the other side and pull it into a historian or something like that. So yeah, there's definitely wireless out there.
Okay. And it sounds like maybe there's still, cost evolution that, why would you have the serial radio if the Ethernet radio was ubiquitous and super cheap, right? You'd always do that. But then you're saying that's not the main bottleneck. That might help, but
yeah, and some of it, I think that's definitely a solution that could be implemented if it was the fix, was to switch radios. For the reason these were serial radios was kind of that the legacy system that managed all these was built on collecting serial data. So we just kept serial radios. There was a point where we went for a bit to not consumer grade, but 3G cellular. But what was happening was, because we didn't run the cellular network, we were leasing off of Verizon or AT&T or whatever. They didn't really commit to how long they would support a particular type of radio. So I think we spent tons of money and tons of time outfitting a ton of stuff with 3G cellular, only for 2 years later Verizon to say, we don't support that anymore. Go upgrade them all to 4G. But the other cool thing about MQTT is that since it's so, the data that's transmitted is so small, you could have really low bandwidth radios. So, oh man, what's it called? Not why. I'll try to remember it, but there is a LoWRAN, LoWRAN is become a really popular type of wireless for especially IoT kind of devices, and that has tremendous range. I think we could cover this entire field with 2 receivers, and this is just a small square of our field.
Another thing which I was thinking about is, do you think it makes more sense to do predictive maintenance on the tools themselves and have it be a little more decentralized? So that way you don't need this huge, large scale data structure within the entire company. And it's more up to the tool and equipment providers to come up with their own very specialized predictive maintenance solutions, and then just send some smaller set of information to the user. Or does
I
that
think
sort of,
it. I think,
because
Go
you
ahead.
mentioned the voltage controllers sort of did that, I think, but you pointed out that that just ends up giving less information to the user in the end, and it's only what the operator needs, and it's only what the operator needs.
Yeah. I think that if that was more common, I think it'd be an option. But another thing is then you're kind of beholden to your vendor on what you can and can't do. So not that we're not beholden when I say we, like I'm still there. Not that we weren't beholden to many, many vendors, like their roadmap kind of drove what we can do. But I would, a lot of like what the architecture for these like kind of PLCs and connected things is that it's very plug and play. So like if you don't like one vendor or one piece of equipment, you can pull that out and put someone else in it and everything will talk and it'll also work. And I think ideally that's what you'd want to see with some of this stuff too. If that did mean it was like a smaller thing that just like read the data you're receiving, it did its own predictive maintenance, like maybe it's trained on a model specific to like whatever Lufkin pump off controllers. Like if it did that, that's fine. But I haven't really seen that kind of like a containerization of softwares like that in industry. And the other thing I'd be worried about is that now they can like charge whatever they want for it. So maybe this is like me on the technical side of things saying I'd rather have the data and be able to choose what I do with it rather than having you tell me what I can have and what I can't after I pay the license. So yeah, I think that would work. I think that would be a vast improvement. I wish it would happen more. So maybe a quick example. We had, like, I keep mentioning vibration on pumps because that's like very well understood. There's the same company that makes these little heart communicators also makes like a tablet with little vibration thingies on it. You put it on like a pump, and it'll give you the vibration spectra. And you can put that into their piece of software, and it'll do all the stuff, tell you the health, all that kind of things. They also sell, instead of that laptop, a wireless transmitter you can put on it and stick those little things on. And it, like, in its own little way, it wraps this data into something that looks enough like time series data. As long as like it's shooting it directly to this piece of software, it works. So like it is kind of a thing for some providers, but then it ends up in that same spot where you have this really interesting vibration spectrum, but it only goes from like the collection point into this piece of software where the only way to get it out is like as a PDF. So it seems to be kind of not missing the point, but you're not getting as much use as you could out of it by saying, well, maybe I can design something better, or I have a different idea. You're kind of beholden to what they give you.
That makes sense.
Well, this is very enlightening and depressing all at the same time. So thank you.
It's job security for sure. I'm just happy I made it this long. I thought I'd run out of things to say at the 30-minute mark. But thank you all for attending and your questions. This was super fun to share some of what I've done with this audience. And any other thoughts or comments come up, definitely feel free to reach out.
Well, the one thought is now we know more about your expertise. We may be coming back to you on, thoughts or something on some other projects. There's a couple that may even be vibration.
As you can tell, my absolute favorite.
Yeah, but yeah, so this is great. Thank you very much.
Cool. Well, thanks everyone.
Thanks.